Let's get started. I am going to start by taking questions from Chapter 6 things. Does anyone have Chapter 6 questions that we want to talk about? Hannah.
Number 10 from the worksheet.
10 from the worksheet. Sure. Okay. So this asks us to use our power reducing identities. So I'm going to go to my power reducing identities page. I know that I don't have to do anything to the angle measure to like get it in the proper form to use a power reducing identity. But I probably want to convert this from radians into degrees just to make our lives a little easier. So let's just do that real quick. So the pi's cancel. 8 goes into 180 4 times. 180 divided by 2 is 90, divided by 2 again is 45. 45 times 3 is 135. And now if I go and I look at my power reducing identities, I don't have one for cosecant. But I remember from last chapter that with R4 that cosecant is the reciprocal for sine. So I can do that. And now I can do my power reducing identity for sine. So I'm going to do that so you guys can see where which division bar was which. Is everybody okay so far, Hannah? You're all right? Now, if I have 1 over a fraction, remember back to like a couple chapters ago when we were graphing the sinusoids, if I had like 1 over 1/2, that was the same as 2, right? It was like just making a reciprocal. So I'm going to do the same thing here and just think about this as like 2 over cosine of 270. So far, so good. And if I'll go to my unit circle now, I'll locate 270 degrees and look at the x-coordinate because we're looking for cosine of 270. And that is 0. So that's just going to come out to be 2 over 1 or 2. Does that feel okay there?
Yeah.
So the cosecant thing, I just used the reciprocal to sine it. Power reducing is the takeaway there. Is that cool? Who's next? Grace.
Number 3.
From the worksheet or the homework? Sure. Oh, excuse me. All right, so here the directions say to use the sum or difference identities, although this one is in radians, so I'm going to start just by converting it into degrees. Because that just usually makes our lives a little bit easier. So the pi's canceled. 12 goes into 180. What is that going to be? 22.5 or something? Let me just do it real quick on my calculator. Oh, 15. I should have known that. Whatever. So we have tan of negative 15 degrees. So I'm going to write that as a subtraction problem. probably feels the most natural. I'm going to write that as 30 degrees minus 45 degrees. Here, because we're doing a subtraction, the order in which I write the subtraction problem matters, right? 30 minus 45 is negative 15, but 45 minus 30 is positive 15. I have to make sure I write them in the right order so I'm getting the right number. So far, so good. All right, I'm going to go look at my sheet. I'm going to look for the sum and difference identity for tangent where I'm subtracting. That's SD6. So that's going to be tan of 30 minus tan of 45 over 1 plus tan of 30 times tan of 45. So far, so good. I'll go to my unit circle. I'll locate 30 degrees. I remember tangent is y over x. So that's going to be 1/2 over root 3 over 2. And then I'll look at tangent of 45, again, which tangent is y over x, which is root 2 over root 2. And then tan of 30, I'm just recopying. And tan of 45, I'm just recopying. Now I notice that root 2 over 2 divided by root 2 over 2 is just 1. And then these guys, like the denominator of 2's, can cancel out because they're the same on the top and bottom. And if I multiply the two fractions in the bottom, 1 times 1 over root 3 is just 1 over root 3. Does that feel okay? So I have two issues now with this answer. I have fractions inside of fractions, don't love that. And I have radicals in the denominator, don't love that. I always take care of the fractions inside a fraction first. So to take care of that, I want to multiply the top and bottom by the denominator of the fraction. And then I just distribute that through. So that's going to be 1 minus root 3 then over root 3 plus 1. So far, so good. Now I still have that radical in the denominator. So I'm going to multiply by the conjugate now. Remember, the conjugate is the same thing, but with the opposite sign in the middle. So that's going to be root 3 minus 1. So I'll multiply that to the top and bottom. I'm going to just... should have been really doing this. Now, I have to FOIL this out. So the numerator, I get root 3 minus 1 squared minus root 3 squared plus root 3. The denominator, though, looks like a difference of 2 squares, right? I have like an a plus b times an a minus b. So I can shortcut that. I know that's just going to be a squared minus b squared. Or if you don't remember that or you don't like doing that, you can FOIL it out. You'll get the same answer either way. Me, I'm just like looking for those extra little edges of efficiency to make my life a little bit easier. So the radicals cancel with the squares. In the numerator, I'm going to have negative 1 minus 3, so that's going to be negative 4. In the bottom, I'm going to have a 3 minus 1, so that's going to be a 2. And then also in my numerator, I'm going to have 1 root 3 plus another root 3. That gives me how many root 3's? 2 of them, yeah. So I have plus 2 root 3. At that point, I notice that, hey, all the coefficients are divisible by 2. So I can reduce that if I just kind of break that one fraction into two fractions with a common denominator. Negative 4 divided by 2 is just negative 2. And then the coefficients of 2 cancel out. So my final answer should be -2 plus root 3. And again, remember, you can check all these guys on the calculator, right? Even Hannah, the one that you asked about, we could have checked. I forgot to check it. We'll check this one, though, because I thought about it. So we had, what did we have? We had tan of -15. Make sure I'm in degree mode. Whoop! Wasn't there. So tan -15. And then -2 plus root 3. What's that tell me? I did it right, because the numbers were the same, right? So again, to check this, what I'm doing is I'm typing the original problem into my calculator, and then the answer I get into my calculator, making sure I have the same decimal. That's what I'm doing to check them. All these chapter 6 problems are checkable. No reason you should ever finish a chapter 6 problem and not know for sure whether you've done it right or wrong. Well, at least not know if you have the right answer or not. Maybe you did it wrong and somehow managed to get the correct answer still. That can happen. But that's probably uncommon. Grace. Okay. Anybody else? Questions on Hannah?
Did you do 11?
11? Probably. Okay. So again, same kind of story, right? We don't have to convert this radians to degrees. So we're going to use and I'm going to do this in one step. Is that okay with you, Hannah? I'm going to do R5 along with power reducing number 2. So all I'm doing now is I'm going to do the reciprocal of power reducing 2. You notice if you look at your identity sheet, I flipped the power reducing 2 because secant is the reciprocal of cosine. So I just used the reciprocal of that identity. Okay, 2 times 67.5 is 135. So I'm going to go to my unit circle and look up cosine of 135. Remember that the cosine is the x coordinate, so that's negative root 2 over 2. That answer I look at and I go, shucks, I got a fraction inside of a fraction. Well, I'll just multiply by the denominator of the little fraction to take care of that. When I do that, I get 2 over 2 minus root 2. So far, so good there. And then, shucks, I got that radical in the denominator still. So just like we did on Grace's problem, I'm going to multiply by the conjugate. The good news here is, though, that I don't have to FOIL out the numerator because the numerator is just like one thing. It's not 2 terms. Well, that's nice, Mr. Kulik. So I suspect I'm going to be able to reduce, so I'm not going to multiply the numerator out right away. I'm going to use that difference of 2 squares factoring pattern to multiply the denominator out. You could FOIL it if you wanted to. That'd still be okay. The square cancels with the square root. So I have 4 minus 2. So that's 2 on the bottom. And whoop, whoop. Those guys reduce. So I'm left with just 2 plus root 2. Or if you had distributed the 2 through, you just break it up into 2 fractions and reduce each fraction. It's fine. I kind of saw what was going to happen, so I just refused to multiply the numerator out and save myself a little bit of hassle, but it's very little. So. Yeah, of course. Does that feel okay? Good. Good. All right. You guys ready to see some new stuff here?
Yeah.
Yeah, let's do it. Let the learning begin. All right, I have to do this. This is driving me nuts. There we go. So, chapter 7 is what we're going to be starting today. So, to start here, I want us to go back into first semester for a moment. So remember, one of the kinds of problems we did in first semester, we asked you to solve a triangle. What does it mean to solve a triangle? You want to find all the angle measures and all the side lengths. In first semester, we did this for right triangles. The two tools that we used were SOHCAHTOA and the Pythagorean theorem. In second semester, right now in chapter 7, we're going to worry about non-right triangles. In a non-right triangle, SOHCAHTOA does not work. And the Pythagorean theorem does not work. One of the most common mistakes students will make is using right triangle techniques on non-right triangles. I'm going to make a point of trying to trick you into saying, do the Pythagorean theorem over and over and over again in situations when you can't, to keep reminding you that you can't be doing that. Everybody's okay with that? So what are we going to use then, Mr. Kulik? Well, in chapter 7, we're going to look at two new formulas, and those will be our tools. The first one is the law of sines, which I'm going to abbreviate LOS. And the second is the law of cosines, which I'll abbreviate LOC. So in chapter 7, largely we're going to be working on solving non-right triangles. You're going to have two tools at our disposal, the law of sines and law of cosines, in order to do this. The first step is figuring out which tool to use. So that's the first part of what we're going to talk about today. So to solve a non-right triangle, you need to be given three pieces of information. You can either be given two angles and one side, Now, those two angles and the one side that you're given, you can have the one side be in between the two angles or the one side outside of the two angles, right? Does everybody see the two possibilities that we have here? Remember back to geometry, I know that was a long time ago, you guys would have talked about triangle congruence. Specifically, there are triangle congruence theorems that were named with 3 letters, like angle, side, angle, and angle, angle, side, and side, angle, side, and side, 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 and stuff like that, right? Does that ring a bell?
No, angle, side, side.
We're going to be naming these situations for solving non-right triangles using those same abbreviations. So if I look at our first triangle, the triangle on your left, how would you name that triangle using like those 3-letter abbreviations? That is angle, side, angle. Very good. Because we have an angle, and then in between it is a side. Actually, let's angle, side, angle. Right? If we read it counterclockwise or whatever there, we read it as angle, side, angle. Everybody agree? What will the other one be? Or the triangle on your right? Angle, angle, side. Again, if we read it counterclockwise there. Is everybody okay with picking out the difference between these two? This will be critically important. It is one of our first steps in solving one of these non-right triangles is to decide which one of these situations we're landing in so we can choose our formulas appropriately and use the proper technique in order to solve that situation. Okay, so it is critically important that you're able to look at a picture and identify, is this like angle, angle, side, or angle, side, angle? So far, so good? So another possibility, you could have one angle and 2 side lengths. I don't know. Okay. Again, using those 3-letter naming conventions that we did for our geometry congruence theorems, what is that first triangle? How would we name that? Very good. Side, angle, side. Again, because if we look at this, we have our angle in between the 2 sides, right? What would this second situation be? Side, side, angle. Again, because the angle is outside of the 2 sides. Is everybody still feeling okay? The third possibility is you're given 3 side lengths. This should be the easiest one to identify because there's only one way to draw it. It's always going to be a side, 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 right? Is there an angle, angle, angle situation? You'll never be able to solve an angle, angle, angle triangle because the side lengths, well, there's infinitely many triangles that have different side lengths, but the same 3 interior angles, right? For example, if you had a 45, 45, 90 triangle, the side lengths could be 1, 1, square root 2. They could be 2, 2, 2 times square root 2. They could be 3, 3, 3 times the square root of 2. And I could keep going and enumerating infinitely many of these that are all still valid 45, 45, 90 triangles. So that's not something you would have to do. Are we feeling okay about how to identify the situation? Is this all right so far? We'll do some more practice as we get into specific examples. But this is a necessary skill that we have to be able to do. It's a pretty easy skill because it's building on something you did in geometry where you had to recognize these scenarios also, but geometry was a long time ago for some of us. All right. So for the ASA, AAS, and SSA cases, we're going to be using the law of sines. For the SAS and SSS situations, we're going to be using law of cosines. Now, like if we were in the honors class or whatever, we would derive the formulas for the law of sines and law of cosines. We're not going to do that in here. I'm just going to state the formula, and then we're going to move on and practice using it. Actually, I'm going to write that a little bit differently. So the law of sines here is really 3 formulas. We're just going to write it all as one, though. What the 3 formulas are, you can say that these 2 ratios are equal to each other. You could say these 2 ratios are equal to each other. Or you can say these 2 ratios are equal to each other. Right? Basically, this formula just says any of these 2 ratios you can set equal to each other, and that's your equation. We're just writing it this way for compactness sake. Does everybody get what I mean here? All right, I'm going to erase all that because it just muddies up the thing. Okay. So here we're going to be asked to solve the triangle. We're given angle A is 32 degrees, angle B is 73 degrees, and side C is 13 degrees. My first step will be to draw and label a triangle. Now, I never get fancy about it. I draw all my triangles so they look the exact same. They all just look like an equilateral triangle. I don't really care about drawing them to scale. I never bother to try because it just seems like it's never worth the effort. Is everybody okay with that idea? I'm going to go ahead and label the vertices of this triangle A, B, and C. It doesn't matter the way I order the A, B, and C as long as I have one label per vertex, right? However, it definitely matters the order in which I name the side lengths. Does anybody remember from first semester the convention that we need to use to name the side lengths? So if I look at angle A, the side opposite angle A, I need to name as little a. Does everybody see that? If I look at angle B, the side opposite angle B needs to be named little b. And then the side opposite angle C needs to be named little c. You guys remember doing this first semester? We talked about naming triangles like this first semester, doing these same kinds of problems. Critically important that you're naming your triangles correctly. If you goof up where the side A and side B go, for example, your answers are going to be cuckoo crazy all over the place and not work out just because of labeling issue. Okay, so you have to be able to do that. Do you guys understand what I mean by how to label this correctly? Okay. All right. So now I'm going to add in the values that are given to me. Angle A is 32 degrees. Angle B is 37 degrees. And side C is 13 inches. What situation am I in? It's angle, side, angle. Excellent. Which means that I'm going to be using the law of sines. So far, so good. Remember, the goal here is to solve the triangle. That means I want to find all the missing side lengths and all the missing angle measures. So I have one more angle to find and two more sides to find. One of those three things is almost always going to be super easy to get. Do you guys see which one of those three things here is going to be super easy? I don't even need to use the law of sines to get it. Does anybody see what it is? How many degrees are in a triangle? 180. So if I know two of the three angle measures, should I be able to find the third? Yeah, right? So I know that angle C should be 180 minus 73 minus 32, or 75 degrees. So I'm going to add that into my picture now. If I can do that, I want to do that straight away. Whenever I'm given two angles, or as soon as I get two angles, I'm going to just find the third one using that same process, 180 minus the other two. Everybody's good with that? That's one answer. Now, to get a side length, I have to use the law of sines. So to look at the law of sines, what I want to do is look for a situation where I have the angle measure and its side length. So I'm going to look for either, do I have angle A over and side A? Do I have angle B and side B? Do I have angle C and side C? So let's look at our picture. Which one do I have both the angle and the side for? C, right? I know side C is 13. And I know angle C is 75. So I know when I use my law of sines, I'm going to use the ratio sine 75 over sine 13. Now I need to make a choice. Should we solve for angle A first or angle B first, or does it not matter? In an angle side angle situation, it does not matter. I'm going to choose to do alphabetical order, and I'm going to find side A first. So I'm going to complete the other part of our law of sines to say sine of angle A over side A. Is everybody okay there? What is this equation called when I have one fraction equal to another fraction? Do you guys remember what this type of proportion? Very good. Do you remember how to solve a proportion? Cross multiplication. Remember, cross multiplication is a solving technique, not a way to multiply fractions. So if we cross multiply, we have a times sine 75 equals 13 times sine 32. Is everybody okay with how I got there? To get the a by itself, I just need to divide both sides by sine 75. And now it's calculator time. Now, first thing I do before I start typing anything into my calculator, I should
Make sure it's the right mode.
check the mode. What mode should my calculator be in for this kind of a problem?
Degrees.
Degrees. How did we know that?
Because we have degrees of the problem.
Because the angle measures were in degrees. Excellent. So let's check that real quick. I just changed it to degree today, so I know I'm all set. So I'm going to do alpha y equals and choose the first option to make that fraction bar on my calculator. Now I can type in my equation just like it looks on my sheet of paper. So 13 times sine 32 divided by sine 75. If I press enter, I get 713. Now I have two of the three sides for my triangle, correct? To find the third side, I can just do the Pythagorean theorem, right? No! Why not? It's not a right triangle. I tried to trick you and you were paying attention. I appreciate it. I'm going to try to do it a bunch more times, so make sure you're paying attention. All right. So what should I do then? I'm just going to do the law of sines again. I'm going to repeat the same process I just did. So I'm going to do sine of 75 over 13 equals, this time I'm going to use sine of angle B over little b. Quick aside, instead of using sine 75 over 13, could I use sine of 32 over 7.13? Yes. I never do that because if I make a mistake here on the 713, this next problem would be wrong because I had the wrong answer before. The first one, I'm much more confident in my ability to subtract three numbers and get the correct answer, more so than apply the law of sines correctly. So given the choice, I'll use this one, which I feel much better about. The other reason is the 713 is a rounded answer. So I'm going to be a little bit more accurate if I use this one because the 75 is an exact value. All right, anyway, so let's keep on going. Cross multiply. So b times sine 75 equals 13 times sine 73. We'll divide both sides by sine 75. So B is 13 times sine 73 over sine 75. Now it's calculator time. So I'm just going to go and take that last thing that I typed in and just update the 32 and change that to a 73 and just press enter again. Save myself some buttons. So I get 1287. My last step now is I'm going to go back to my original picture here and write in my values. So side A is 713, side B is 1287, and I'm going to do a quick little check. Now the check I'm about to do is not perfect. It doesn't catch every possible mistake, but it'll catch a lot of them. What I'm going to do is make sure that my biggest angle is opposite my biggest side. Yup. That my middle angle is opposite my middle side or middle-sized side. And then my smallest angle is opposite my smallest side. That's not a guaranteed check, right? If I had like transposed the numbers and wrote like 12.78 instead of 12.87, I'm not going to catch that kind of a mistake. But if I mislabeled my picture, oftentimes I will catch that. AJ. Sure. I'm pretty sure he can. He's requested to do it before. So, and then he came back. So at least, I assume that he's able to do it. All right. Everybody feel okay with that first example? Let's do another. Okay. Say we have angle P is 43, angle Q is 80, and side Q is 7.3. So first step is to draw ourselves a picture. What should I label the vertices for my triangle here? What do you guys think? It's not a hard question. So P and Q definitely. How about what should the third one be though? Just the alphabet, guys. R, I think, right? Are you a pirate?
Yeah.
Okay. Yo ho ho. All right, and then we need to label the side lengths, right? So little p, little q, little r. Again, be careful about how you're labeling those. Again, the side opposite the angle has to have the same letter label as the angle, right? So I'll go ahead and write in my values that I was given and then ask myself, what situation is this? Which one of the 5 situations is this? Angle, side, angle, 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 side, side, angle, side, 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 angle, or side, side, side. Nobody objected when I asked them if they could do this, and now nobody wants to do it. Somebody take a risk. What is it, Nora? That's correct. Which tells me I need to be doing law of sines. And because I already have two angles given to me, what should I do first? If I already have two angles, as soon as I have two angles, what should I do? Find the third. How do I do that? Yeah. So 180 minus the other two. Go ahead and write that answer in since I'm right here. To find the other two side lengths now, I'm going to use the law of sines. Which angle side pair should I use? Q, right? Because I know angle Q and I know side Q. Everybody see that? So that's what I'll start with. So I have sine of 80 over 7.3. And again, it doesn't matter in this situation either which angle we solve or which side we solve for first, P or R. I'm just going to do alphabetical and solve for side P first. Got to have some kind of reason why you did it. I'll use the alphabetical. We'll cross multiply. Actually, I'm going to just do the cross multiply and divide all in one step. Is everybody okay with me doing this? We've done two examples of like how I'm doing that. I hope it's okay to just condense some of this work. If you're not good at doing that, again, feel free to write out more steps, like show more work. Take it a little slower if you don't feel confident. That's not what I said. There we go. Yes. Oh boy. So I get 506. And then we'll repeat. Again, I'm going to use that same initial ratio. But this time I'm going to use angle R over side R. We'll cross multiply and divide. Go to our calculator. And again, what I'm going to do is I'm just going to go and take the last thing I entered in and just update the 43 to be a 57 and save myself a whole lot of button pushing. And that gives me 626. And the last thing I'm going to do now is write in these last couple of values onto my picture and do my little check. Right? So P is 506 and R is 626. And I notice the biggest side is across the biggest angle, middle length side across from the middle sized angle, smallest side opposite the smallest angle. So I feel pretty good. You guys feel all right here? Okay. So far, so good. That would have been section 7.1. I'm going to skip 7.2 for right now. We'll circle back to it. We're going to do 7.3 and the law of cosines next. In case you're looking in the textbook. 7.2 is the hardest section in the chapter, and I think it'll go a little bit better if we have done a little bit of this practice before we do that. So our law of cosines, there's like 3 versions of it. You know, so if I have just some non-right triangle, I can say a squared is equal to b squared plus c squared minus 2bc times cosine of A. Or I can say b squared is equal to a squared plus c squared minus 2ac cosine of angle B. Or I can say, well, let's put an angle sign in here. Or I can say c squared is equal to a squared plus b squared minus ab cosine of angle C. What do these formulas all look like to you guys? No. Looks like the Pythagorean theorem, right? Like if I just looked at
That's what I meant.
that part of it, it's like the Pythagorean theorem with this extra correction factor. If we were to prove this or derive this formula in class, which we're not going to, we'd be using the Pythagorean theorem for that derivation. But we're not doing that. We're just going to state it and use it, and that'll be the end of it. Yes, of course. Okay, so new example, solve the triangle. First step, I'm going to draw myself a picture. Label my triangle angles A, B, and C. So side A, side B, side C. Add in my values, 34 degrees, 14, 17. What situation is this? Lexi says side angle side. She's correct. That tells us we need to be using the law of cosines here. So if I look at my three formulas, I'm going to look for the one where I have to use angle A. That's the first one. So we're going to say that we have a squared equals b squared plus c squared minus 2bc cosine of angle A. So if we fill things in, we have 14 squared plus 17 squared minus 2 times 14 times 17 times cosine of 34 degrees. Now, for the love of all that is holy, just type this in one line in your calculator. Don't chunk this and do like 14 squared and then 17 squared and then 2 times 14 times 7 and like get all these little just type it into one line in your calculator and press enter. You're way less likely to goof up some order of operation if you just let your calculator handle it. You wrote it down exactly like it should appear in your calculator. Just type it into your calculator here. Now, Mr. Kulik, that can't possibly be right. Side A is not 90.37. What's going on here? Who sees it? What did we solve for here? A squared. How do we get A then? Square root, right? So again, square root, and I'm going to press second and the negative sign. That just gives me the ants command. That's the last answer your calculator found. So I get about 90.51. Or 9.51, excuse me, 90. Yes. Everybody okay now? All right. So now we need to find either angle B or angle C. This time the order matters. We need the smallest of the two angles first. So which angle is going to be the smaller of our angles? B or C? Which angle is going to be smaller, angle B or angle C? Come on, guys. What do you know about angles and side lengths? The smallest angle is opposite the smallest side, right? So look at the side lengths for B and C. Which angle is going to be smaller? B. Everybody's good with that? Okay. So to find angle B, I could use the law of sines now, because now I have, like a enough to do that, enough information to do that. Or I could use the law of cosines again. I would do the law of sines because finding an angle with the law of sines is a lot less of a hassle than with the law of cosines. So I'm going to do sine of 34 over 9.51 equals sine of angle B over 14. So far, so good? Okay. I'm going to cross multiply and divide. That's going to give me sine of B equals 14 times sine 34 over 9.51. How do I get rid of that sine B there, though? Or that sign in front of B? What cancels out that sign? Who remembers how to cancel that out? Anybody? Oh, guys, it's sine inverse. So you do sine inverse to both sides. And now it's calculator time. So second, sine inverse, and then alpha y equals, to get my fraction command, 14 times sine 34. And then I'm going to just use my ants command to grab that 9.51 and press enter. So I get about 55.44 degrees. Everybody good there? All right, we still need angle C. How am I going to find that? Oh, come on, guys. I just found angle B. I already have angle A. Not the Pythagorean theorem. That solves side lengths, but it doesn't work here because it's not a right triangle. How about 180 minus angle A minus angle B? Right? Shouldn't that do it? Remember, always should get one value. One of the angles you're going to find is always going to come from like that little trivial thing. So 90.56. So far, so good? Okay. I'd go back and write these in our picture to check them, but I'm going to skip doing that in the interest of time. Our last example now. Side P is 5, side Q is 8, side R is 10. Now, clearly what kind of situation is this? Side P is 5, side Q is 8, side R is 10. Clearly this has to be side, side, side. I just have 3 side lengths. That's the only possibility, right? In the side, side situation, we must be careful. So, a triangle is not always possible. Just because I give you 3 numbers doesn't mean you can make a triangle out of it. Right? If I tell you the side lengths are 1, 1, and 10,000, not going to be able to make a triangle out of that. They're not ever going to be able to, those 2 little tiny short sides can't, ever reach. So we have to check this. So our check is that leg plus leg has to be greater than the hypotenuse. How do I tell which ones are legs and which ones are hypotenuse from 5, 8, and 10? Dude, the hypotenuse is the longest side. Which one's hypotenuse? It's 10, right? So 5 plus 8, is that greater than 10? You betcha. So this is possible. Okay. So now I'm going to draw my picture. Well, maybe I should do that. I've been doing that every time. Okay. Now, I have 3 angles to solve for. Once again, have to be careful. In a side-side situation, we have to find the biggest angle first. What angle is the biggest angle? R. How did you know it was R? Because the side R is the biggest side. So I'm going to write out my law of cosines here, but I'm going to do it without plugging the numbers in for a moment. Because what I want to get is I want to get that angle R by itself. So I'm going to solve this equation for r with the letters in it first, and then plug the numbers in after I've got the r by itself. So I'll start by subtracting p squared from both sides. So I'm going to have r squared minus p squared equals q squared minus 2pq cosine r. And then subtract q squared from both sides. So now I have r squared minus p squared minus q squared equals negative 2pq cosine r. And I'll divide both sides by negative 2pq. So I have r squared minus p squared minus q squared divided by negative 2pq. And then I'll do cosine inverse of both sides. To get rid of the cosine. So I have r equals cosine inverse of r squared minus p squared minus q squared over negative 2pq. So when I plug my numbers in, cosine inverse of 10 squared minus 5 squared minus 8 squared over negative 2 times 5 times 8. Again, please just do this in one line on your calculator. That fraction command where we put the fraction bar in your calculator will help enormously because the parentheses on this are a bear. So cosine inverse, and then just typed in my formula. Press enter and I get 97.90. Is everybody okay here? If I look, this is now like a side angle side situation here, right? That I'm solving where I have two angles to solve for. Doesn't that kind of look like the side angle side? What was the rule for a side angle side? We have to find the smaller of the two angles next. And I'm going to use the law of sines to do that. So I'll have sine of 97.90 over 10 equals sine of p over 5. Cross multiply, divide, and then do sine inverse. I'm going to do that all in one step. Is there any objections to me doing it that way? Again, if you're not comfortable doing all of that all at once, please take multiple steps. If you never get comfortable doing it all at once, you don't ever have to. I've literally done these kinds of problems like tens of thousands of times in my life, so like Mr. Kulik feels real good about what he's doing. If that's not you, don't pretend like it is. Just do it at the pace you're comfortable at. Notice that I use the ants command there to get the 97.90. So I have 29.69. And then angle Q, how am I going to find that? I have two angles now. So I can just do 180 minus the other two. So 180 minus this one minus this one. 5241. Those should be my 3 angle measures. It's stopping time for Mr. Kulik. That felt like a lot today. What I'd like for you guys to work on is in chapter 7, you're going to do numbers 1 through 4. And then you're going to do 15 to 22. And from chapter 6, remember we had already assigned 1 through 10. It was like 23 to 26 and worksheet 1. All of this would be due Sunday. What I assign on Friday wouldn't be due until the following week, but these are what's due Sundays. Any questions so far about like what's due when or what we're doing next or any of this jazz? Doing okay? How did today feel? Should have felt pretty okay. This is not like, some of the problems are like lengthy because there's lots of things to do, but the individual steps to do them are like the same kind of thing over and over and over again, which shouldn't be too bad. Notice that today we talked about the AAS, ASA, SAS, and SSS cases, how to do those. Which one haven't we done yet? SSA. Now, if you remember back to your geometry course, there is no SSA, triangle congruence theorem. That's what makes that case the hardest possible case, because lots of weird things can happen. We'll deal with that all next time. But that's going to be it for me today. How you guys feeling? Tired?